this module, you will learn more about the molecular orbital theory. As we have learned, molecular orbitals are obtained by combining the atomic orbitals of the atoms in a molecule. For example, in the hydrogen molecule, each atom has one electron in its 1s orbitals. These two 1s orbitals come together to form two molecular orbitals. One of these two molecular orbitals is formed due to the constructive interference of the two 1s wave functions, and the other is formed due to the destructive interference of the two 1s wave functions. The molecular orbital formed due to constructive interference is called a bonding molecular orbital, as the electrons belonging to it are placed between the two nuclei. This stabilizes the molecule. The molecular orbital formed due to destructive interference is called an anti-bonding or sigma star molecular orbital, as the electrons belonging to it are placed away from the region between the two nuclei. This increases their energy, thus making the molecule less stable. Just as in atoms, electrons in a molecule too first occupy lower energy levels. Thus, we find that the two electrons of the hydrogen molecule first occupy the sigma bonding molecular orbital. This lowers the overall energy of the molecule compared to the isolated hydrogen atoms. Molecular orbitals not only help us determine the stability of molecules such as hydrogen, they also help us understand why certain molecules such as the helium diatomic molecule do not exist in nature. You see, helium atom has two electrons in its 1s orbital. When two helium atoms come together to form a molecule, the 4 electrons would be distributed across both sigma bonding and sigma star anti-bonding molecular orbitals. The energy of the sigma bonding molecular orbital will be low. However, the energy of the sigma star anti-bonding molecular orbital will be considerably higher. Thus, the overall energy of a helium diatomic molecule will be the same as that of two helium atoms. So, there will be nothing holding them together. Hence, the helium diatomic molecule does not exist. 4 molecules formed by atoms containing more than 2 electrons. We will only consider the molecular orbitals formed by their valence shell and not the ones formed by their core orbitals to understand their stability. Now let's study the molecular orbitals formed in an oxygen diatomic molecule. Oxygen has the atomic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. When two oxygen atoms come together, their 1s2 atomic orbitals combine to form 2 molecular orbitals. Their electrons are concentrated along the bond axis. Hence, they are called sigma 1s bonding and sigma star 1s anti-bonding molecular orbitals. The two 2s orbitals combine to form sigma 2s bonding and sigma star 2s anti-bonding molecular orbitals. Two 2pz orbitals too combine head-on to form sigma 2p bonding and sigma star 2p anti-bonding molecular orbitals. However, the two 2px and 2py orbitals combine sideways to form a p orbital shaped bond with the electrons concentrated either above or below the bond axis. Hence, these molecular orbitals are called pi orbitals. The two px atomic orbitals combine to form pi x bonding and pi star x antibonding molecular orbitals, whereas the two py atomic orbitals combine to form pi y bonding and pi star y antibonding molecular orbitals. As the energies of the two px and two py atomic orbitals are the same, the energies of pi x bonding, pi y bonding molecular orbitals and pi x star antibonding, pi y star antibonding molecular orbitals are the same. Thus, the interaction between the valence shells of two oxygen atoms leads to the formation of 8 molecular orbitals: sigma 2s, sigma star 2s, sigma 2p, sigma star 2p, pi x, pi y, pi star x and pi star y. Due to the difference between 2s and 2p atomic orbitals, the resultant molecular orbitals sigma 2s and sigma star 2s lie below the other 6 orbitals. Due to the head-on bonding between 2pz atomic orbitals, the interaction between them is stronger than the 2px and 2py orbitals. As a result, the sigma 2p orbital lies below the pi x and pi y orbitals, and the sigma star 2p orbital lies above the pi star x and pi star y orbitals. While this sequence of molecular orbitals is accurate for molecules such as oxygen and fluorine, but not for other elements such as boron, carbon and nitrogen, the molecular orbital's energy sequence is slightly different. This is because of the interaction between the electrons of the 2s atomic orbitals of one atom with the electrons of the 2pz atomic orbitals of another atom due to their relatively similar energy levels. In these molecules, the energy level sequence is sigma 2s, followed by sigma star 2s, followed by pi x and pi y that are at the same energy levels, followed by sigma 2p, followed by pi star x, pi star y, and finally sigma star 2p. As we know, the number of bonds between a pair of atoms is called the bond order. In terms of molecular orbitals, to calculate the bond order, we assume that 2 electrons in a bonding molecular orbital form one bond, and that 2 electrons in antibonding molecular orbitals cancel the effect of one bond. Thus, we can calculate the bond order in an oxygen molecule using the formula bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. Now, in oxygen, the number of electrons in the bonding orbitals is 8, and the number of electrons in the antibonding orbitals is 4. So, adding these values to the equation, we get the bond order as 2. As we know, when electrons in an atom or molecule are paired, as in nitrogen, they form a dimagnetic atom or molecule. And when the electrons in an atom or molecule are not paired, as in oxygen, they form a paramagnetic atom or molecule. In this way, the molecular orbital model helps us understand the structure and properties of molecules. You have now reached the end of this module. In this module, you learnt that molecular orbitals are obtained by combining the atomic orbitals of the atoms in a molecule. The molecular orbital formed due to constructive interference is called a bonding molecular orbital, as the electrons belonging to it are placed between the two nuclei. Sigma orbitals stabilize a molecule. The molecular orbital formed due to destructive interference is called an anti-bonding or sigma star molecular orbital, as the electrons belonging to it are placed away from the region between the two nuclei, making the molecule less stable. As in atoms, electrons in a molecule too first occupy lower energy levels. For molecules formed by atoms containing more than 2 electrons, we will only consider the molecular orbitals formed by their valence shell and not the ones formed by their core orbitals to understand their stability. The bond number obtained by using the molecular orbital model is different from the bond number obtained using the Lewis structure, because in the Lewis structure, all the electrons are paired, and here 2 of the electrons are unpaired. When electrons in an atom or molecule are paired, they form a diamagnetic atom or molecule, and when the electrons in an atom or molecule are not paired, they form a paramagnetic atom or molecule.